Okay, so here we have um, a problem dealing with velocity and acceleration, and we're told that the speed of a car traveling in a straight line is reduced from 45 to 30 miles per hour in a distance of 264 feet. So we want to find the distance in which the car can be brought to rest from 30 miles per hour, assuming the same constant deceleration. Okay, so this problem, I'm just going to let you know, is actually a lot more involved and complicated and fun than you may think. So I'm going to go through it as clear as I can, but really make sure that you make sure you go through your work very step by step, because little details can screw you up here. Okay, so the first thing, let's just change our units into feet per second, because trust me, like it's gonna make the answer a lot easier to work with, because we're given a distance of 264 feet. So we're gonna change 45 miles per hour and 30 miles per hour into feet per second. So let's go from the speed of a car, which we're gonna use the velocity function. So we're gonna have the v of 0, the initial speed is 45 miles per hour. And a later time, we're going to say v of t1, the velocity of time t1 is 30 miles per hour. Converting these to feet. Remember, if there's 5,280 feet in a mile. So what you essentially want to do is take the number of seconds in an hour and convert this from the number of feet that this will travel in an hour. So if it's 45 miles per hour, this would basically do 45 times 5,280 feet per hour. But we're going to divide this by 3,600, because that's how many feet per second it would be. 45 miles per hour is the same as 66 feet per second. And likewise, 30 miles per hour, 30 times 5,280 divided by 3,600 be 44 feet per second. Okay, now we're given that it goes 264 feet from time 0 to time t1. So let's say that its position at time 0 is 0, and then its position s of t1 at t1 would be 264. Now the acceleration a of t, we were saying it's a constant deceleration. So it's the acceleration function. We can start off by just saying it's going to be a. And from here, let's try to figure out what we want to what we're trying to ultimately get in like a mathematical equation. We're trying to find the distance or the position of the car at some time t when its velocity is 0. So we want to find when v of t equals 0. This is ultimately what we want to figure out. Because that's, again, it's going to be brought to rest. And from there, then we can figure out, if we can figure out the time that it is at if we can figure out the time that its velocity is 0, from there we can then figure out how far it's traveled. So let's go from understanding how we can integrate. So the integral of acceleration from, let's say, 0 to t1. So the integral of a of t dt is going to be equal to v of t1 minus v of 0. And then the integral from 0 to t1 of v of t dt would be s of t1 minus s of 0. Now, let's make some equation for velocity and acceleration and position. We have an equation for acceleration, but we're just gonna say it's a because we're told it's a constant. Now, velocity, we can go ahead and say that v of t will be, if we integrate this, because that's what we would get to integrate the integral of a of t, we would have at plus some constant c1. Now that constant is just going to be the initial velocity, because when you plug in 0 into this, all we have is c1. So c1 is just going to be equal to 66. So from here, we can write that v of t equals at plus 66. Now let's look at the position function. From here, s of t would then be, because we would integrate the velocity function to get s of t. So integrating this, we would get at squared over 2, or 1/2 at squared, plus 66t plus c2. Now c2 is going to be the value, or is going to be the position when t is 0, because when you plug in 0, all you're left with is c2. We're told that the position at time 0 is 0, or that's what we're going to use for reference. So then c2 is 0, and then we can just go ahead and write our position equation so far as 1/2 at squared plus 66t. Okay, now what we want to do is use the fact that it travels 264 feet from time 0 to time 1. So then this is equal to 264. So what we can do then is just set this position equation equal to 264 when t is t1. We're going to make t t1 here. So we're going to go from here. Let's make s of t1 is equal to 1/2 a times t1 squared plus 66 times t1. Now, well, we can also use that its velocity at some time, we can say at t1, so v of t1 is 44, so we can set the velocity equation equal to 44 when t is t1. So using that same logic, we can go v of t1 equals 1/2, or not 1/2, it's just a times t1 plus 66. So let me go ahead, and then I actually didn't write that out. So I'm going to v of t1 equals a of t1 plus 66. So we're going to write v of t1 will be 44. And this s of t1, 264. Hate squeezing this in here, but we're going to go with that. S of 264 and 44. So what we're going to do is use these two equations to solve for t1 and a. Once we can solve for t1 and a, then we're going to have an equation for position and an equation for velocity. And from there, we can actually figure out the time that it takes to reach a velocity of 0 and how far it traveled over that time period. So let's solve this. solve these for A. Let's start with this simple one. You can go ahead and say that AT1 equals negative 22. And so A will be negative 22 over T1. So we're going to plug this into here using systems of equations again. We'll have 264 is equal to 1/2. For A, we're going to put negative 22 over T1 times T1 squared plus 66 T1 264 equals to negative 11. Those T1s will cancel down a little bit. Negative 11 T1 plus 66 T1. And we're going to have that 264 equals 55 T1. And then T1 will be 264 over 55, or 4.8. Now that we know that T1 is 4.8, we can find the acceleration, or A, the value of A. From here, we're going to have that A will be just negative 22 over 4.8, which would be negative 4.83, repeating, or negative 4.583. Let me make that clear. Negative 4.583 repeating. Here's my calculator. Okay, so now let's write our velocity and acceleration, or velocity and position equations with A filled in. So we can go and use our velocity equation. So we can write velocity, V of t would be then negative 4.8 or negative 4.583, approximately negative 4.583 t plus 66. And remember, we want to find when V of t will be 0. We want to find the time when V of t will be 0. Because once we figure out how long it takes to get V of t to be 0, in other words, how long it takes for the velocity to be 0, we can plug that time into the position equation and then solve for the distance. So going from here, let's take this one step further. 1/2 times, let's actually fill this in. So then this will leave us with S of t being negative 2.29 t squared plus 66 t. So we have this now. We have this equation for S of t and this equation for V of t. So now we find when V of t is 0. So let's go ahead, let's write V of t is 0. So then making this equal to 0. Why do I keep on messing it up? Negative 4.583 t plus 66. So 66 divided by 4.583 about will give us t that will be 14.4 about, and we're going to make this T2. We're going to call this T2. So it's going to take 14.4 seconds to reach a velocity of 0. Now let's see what its position will be when at that time, like how far it's going to travel 14.4 seconds later. So we're going to plug that into here. So we're going to have S of 14.4 negative 2.29 times 14.4 squared plus 66 times 14.4, 2.29. We're going to get that it goes about 475.5 feet. So it goes a total of 475.5 feet from the initial position, so from 0. But the question may be like asking is find the distance in which a car can be brought from rest from 30 miles per hour. So it basically wants you to figure out how much further it traveled once it was going 30 miles per hour. So we essentially just subtract this distance because when it was going 30 miles per hour, it already went 264 feet. So then we're just going to take away 264 from 475.5. And we're going to get about 211.5 feet. All right, so there you go. Again, really take your time with these types of problems because especially if you're going into physics, it's all going to be about little calculations like this. And I may have, I probably rounded it, a little different than maybe the full solution would be, but that's not an issue. Just again, make sure you can understand it and just take your time and, have fun with it. All right, good luck.